covering all the design sections what we have studied under PRC1 with reference to beam cross sections, singly and doubly, rectangular or T. And I will take one example of concrete structures. Let me first take you to that slide. Analysis and design of continuous beams, and I want to also open one book which I have shared on MS Team with your section. Which was actually the 7th edition of Structural Concrete Theory and Design by M. Nadeem Hussain. So in hopefully in next week you will be on campus, I guess, or next week still is online.
Sir, last week is online also.
So this is the last online week?
No, sir. Next week is last online week. After
Okay.
that, we have mid.
You have mid. Okay, then after mid we will get chance of physical on-campus lecture as well. So in that week I will also discuss the same topic of continuous beams, because this topic gives us a comprehensive review of all the topics covered under the heading of beams, rectangular or T or doubly or singly, not only the flexure but also the shear design. So in this book which I have shared with you, chapter 16 is on continuous beams and frames. So in this chapter 16 you will get idea about the continuous beam analysis and design. So this book is in FPS system of units, but at the end they also provide few examples in SI units, but I will recommend you to also read this chapter 16 as well as the slides which I will share with you, and obviously the concrete structures by Z.A. Siddiqui. That book is also important. So this chapter 16 is also one relevant chapter. Although it covers frames as well, but up to continuous beams you can review, for example 16.2 and up to in this 16.2, under that article you will read up to 16.2.5 movements in continuous beams. So then from 16.3 onward we have building frames, so you will be reviewing 16.1 and 16.2 actually. So let me first start the recording. So 21 students are online. So topic is analysis and design. So analysis means that since it is a continuous beam, and with reference to continuous beams you have studied some classical method of analysis like movement distribution, slope deflection, and we want to discuss that is there any simplified analysis method available which can help us to quickly design the beams which are having uniform spans and subjected to uniformly distributed loads, or we need to follow classical methods or finite element analysis, and then finally to design the cross sections. So this topic actually has two uh, sub topics. One is analysis of continuous beams, and then the second one is design of continuous beams. So up till now, we are well familiar with the strain diagrams and stress diagrams of cross sections. So this slide is just a review of the singly reinforced cross sections where our target is to find out where is neutral axis, and once we have the neutral axis, then we can find out the resultant stresses, and then from the stress diagram we can determine the forces, and knowing their point of application we can finally get the internal capacity. And we know that rather than working on actual stress strain diagram, it is easier to refer to simplified Whitney's uniform stress diagram to find out the resultant compression force present above neutral axis over the area in which concrete is subjected to compression. So this one, slide 16, actually summarizes reinforced concrete rectangular beam cross section which is singly reinforced. And now you have understanding of T-beam as well, which are monolithic cross beams. When you will cast the beams with the slab, and steels are monolithic in a way that the hanger bars or the ties, they are crossing the junction between the slab and the web projected below or projected above the slab, and they are cast monolithic. As you will pour the concrete in the web of the beam, and then finally the slab concrete will be poured. So such cross sections will behave like the T-beam as T-beam cross sections. So when you are casting bare frames, like there is no slab at the stage of casting of the columns and the beams, and finally you will put precast units on the rectangular beams. This is also one structural system in which bare frames are cast, and then later on you are putting the precast slab segments above those bare frames. So in this way there is no integration between the slab and the rectangular beams which are cast in situ. But in normal construction, when beams along with the slabs are poured and the construction is cast in situ, and concrete and the steel present in the beam web along with the shear reinforcement is crossing the junction between the slab and the beam, then the behavior of such beams will become different from the bare rectangular cross sections. However, you have studied that when flange will come in compression and web in tension, then the stresses in the slab and some portion of the web in compression will take the geometry of T shape, and the web projecting below the slab will take the tension. So at such locations where there is a sag and beam is projecting below the slab, like in this case on slide number 18, there is a beam with flanges on top of the web is shown with its deflected shape. So you will notice that at the mid span where there is a sag, tension is in the web and tension cracks are almost approaching the junction between the web and the flange in this picture. So it means above the tip of the tension crack, there is the location of neutral axis at this section. So it means above the neutral axis, there is a compression. So we can conclude that at this situation, when tip of the crack, tension crack is below the junction of the web and the flange, the compression will be present in some portion of the web as well as in the flange. So the cross section, if we draw with reference to section AA, will get this shape that the hashed area is in compression and the geometry is T-shaped. So some portion of the web is also taking the compression below the flange, while the unshaded area is in tension, and we are actually considering the role of tensile steel only in developing the tension force. So strictly speaking, when the slab is above the web and beam is in the sagging region, then the chances are that to determine the compression force, we need to handle the T shape. However, if the neutral axis is present in the flange and it is having the compression, then in the cross section, which is a wide rectangle, so still can that this type of cross section will be like a wide rectangular cross section, because still the compression developed by the cross section is a rectangle, and for tension the steel present on the tension side is only taken and we can state that it will be like C for compression and T for tension. And in this case, equilibrium is again C into T. Here it is a T-shaped compression zone, and here, which is also shown as section AA, but with the propagation of neutral axis up into the flange, has resulted into a rectangular compression zone. So a beam which is cast monolithic with the slab at section AA with the slab present on top of the web may have a behavior as T-shaped if the neutral axis is in the web, and it may behave as wide rectangular beam if the neutral axis is present in the wide flange. And it is important to note that in such kind of T-beams in which concrete is present on top, over the support, if we draw the cross section BB, we will always get the compression in a cross section which is rectangular, while the tension is taken by the steel, and the role of concrete in tension is meager. So we will finally end up over the supports with a cross section which is still rectangular. So behavior wise, you will notice that we have shown 3 cross sections. Out of them, only one cross section, which is shown in picture D, will represent a T-shaped geometry, because we need to calculate the compression force by dividing this geometry into rectangles, and finally we'll get the total contribution of that T-shaped cross section which is in compression. While in picture B and C, although the slab is cast monolithic with the web and it represents a T-shaped geometry, but still behavior wise we will be dealing with the rectangular cross sections. So this was your topic when you studied T-beam analysis and design. And also on slide number 17, we have summarized the strain and stress and force diagram of a doubly beam rectangular cross section. And the only difference is from singly that here in compression zone, the compression steel will also be present, and that will also contribute in the force development on the compression side. And we have the idea that we may end up with case 1 or case 2 doubly beam, which means compression steel at yield or below yield at ultimate stage. Even in case of T-beams, we might come across with a section in which we have a doubly action, and on the cross section which are over the supports, like the section BB, where actually the cross section is behaving like a rectangular beam because compression is taken by a rectangle. So over the supports, if beam is shallow, there are chances that we may end up with a doubly beam slab over the support. So even in this picture, you can consider that this C is developed not only by concrete but also by steel. So it is the two bars which are present are taking part in the development of compression force. So in the above picture, it is also shown that on the edge of the slab, the cross section is L-shaped, and first interior beam running on column center line has the T-shaped geometry, and if slab is resting along two parallel edges, so this slab will behave like the one-way slab because bending will be one way, single curvature. So half of the load will be transferred to this beam and half of it will be transferred to the edge beam. So in load transfer path, this particular slab will behave like one way and 50-50% load will go to the either support. And this cantilever on this side will also transfer its load to this beam. While in case of a simply supported beam, we understand that maximum movement will be at mid-span. So above the crack tip, there will be compression because tension crack cannot enter the compression domain. So I can judge that at this stage neutral axis may be somewhere over here above the tip of cracks. So this portion will be in compression and tension will be taken by the steel. In cantilevers, even if slab is present on top, suppose it is a regular T-beam in which web is present below the slab, so tension will be on top and compression will be on bottom over the support. So that is the reason we are having vertical flexure cracks, and we can easily judge that in this case neutral axis may be somewhere over here below the tip of the cracks. So this portion is developing compression and the steel is contributing in tension over the support. Now question will arise that if we are having 3 to 4 span, more than 1, 2, 3, 4 span beams, shall I be going for analysis of such beams by following any of the classical method like slope deflection, moment distribution, 3-point equation, or I should be referring to some finite element program and I will model my beam on the software to analyze it first, or code guides me regarding some simplified method of analysis for non-pre-stressed continuous beams and also for one-way continuous slabs, because one-way continuous slab over a unit strip will be like a continuous beam because it will also be spanning to more than one spans if there are continuous panels, continuous adjoining panels. So one unit strip will be running panel by panel and it will be like a unit's width having the depth equal to the slab thickness. So it will be like a rectangular continuous beam running over the supports. So ACI in its chapter 6.5 has proposed one simplified method of analysis of such continuous beams and one-way continuous slabs, and it is mentioned over there that it shall be permitted to calculate ultimate moment and shear due to gravity loads. It means dead load due to self weight and live load, which is occupancy load. In accordance with this section for continuous beams and one-way continuous slabs. But this permission is if A through E conditions are satisfied. So the first condition is that members are prismatic. They have a uniform constant cross section. So for non-prismatic members, the proposed simplified method is not applicable. The second condition is these coefficients which are proposed or the simplified method is applicable only and only when loads are uniformly distributed over the beams or slabs. For point loads, for example, if you have a continuous beam and it is subjected to point load rather uniformly distributed, then these coefficients or the simplified method is not applicable. Then you need to refer to some other classical method. So just hold for 1 minute, please. अभी ये मामला फाइनल नहीं हुआ जब तक ये कमेंट्स नहीं आ जाते, क्योंकि हम इनको आउट ऑफ प्रिंट को हम एक्सक्यूज कर सकते हैं कहीं। इस पर हमें एक कंबाइंड पॉलिसी बनानी पड़ेगी कि DR रिलीज करनी है कि, तो इसको अभी होल्ड करें। मेरे पास दिखा रहे हैं इनको हमारी उनको हाँ उनको भी दिखाएंगे, उनसे कमेंट्स लेंगे, फिर हम प्रोसेस करेंगे। आप साल बाद इनकी को लेने की वो दोबारा एग्रीमेंट करेंगे। तो ये कहते हैं आप इसके में से दिखा रहे हैं कि हमारा ये का साल बाद होता है, ये हमारा अपना पॉइंट ये रेगुलर बजट बजट बोर्ड में इससे वो साल बाद वो होती है, ये हमारा अपने पास दे रहे हैं। हर साल बाद दोबारा वो दोबारा हर साल बाद हाँ हमारा ये रेगुलर बजट ये रेगुलर हमारे पास इसकी छुट्टी आपने लगाई थी साहब, इसमें लेटेस्ट डेट कहा था कि इसकी वो में कहा तो मकसद ये हमने जरूरत नहीं है ना, जिसमें ले तरीके से मिले फिर भाई तो हर सारा ये बता किसी पेज पे ये वाला कोटेशन वो भी मेरे पास कुछ होगा दोनों केस ये बस उसको दे इसको कमेंट्स आप तो फिर आज मीटिंग मार गया Okay, please let me resume. The second condition is that live load, service live load over dead load ratio should not exceed 3. So maximum it can be live load or dead load ratio can be equal to 3. So the coefficients which are actually proposed will remain safe if this ratio between live over dead is not exceeding 3. So this simplified method is permitted if there are at least 2 spans. So for 2 or more spans, this is applicable. Last condition is that the longer of 2 adjacent spans does not exceed the shorter by more than 20%. So there is another, you can say, requirement that preferably all the spans should be equal in continuous beams or continuous slabs. But if they are having different spans, then the difference between them should not exceed by more than 20%. And you need to calculate it that the longer of the two adjacent spans does not exceed the shorter by more than 20%. So we will apply all of them in solution of one problem where we will be checking all these conditions in order to apply the ACI proposed simplified method of analysis of continuous beams. So in order to understand this simplified method, this slide 21 is very important. In this slide, terminology is summarized in picture A, and in this terminology you will find that they are naming last span as end span and all other spans as interior spans, and the last edge is named as discontinuous end, and the face on the discontinuous end is named as interior face of exterior support. So this is actually the interior face of the exterior support, and this will be named as exterior face of first anterior support. So it is first interior support and its exterior face, while all other faces, this one, and if it is continuous further, it is not the edge span or the end span, it is still continuous, then all such faces are termed as faces of interior supports. So in text one, once you will find that they are reporting some coefficient, terminology will be used in various textbooks, that they may mention a coefficient at exterior face of first interior support is 10, like it is mentioned over here. So you will be then actually given with the coefficient to determine the negative moment, hogging moment at the exterior face of first interior support. So actually, you know, for simply supported beam, single span, simply supported beam coefficient is 1/8. And then you have to multiply it with the uniformly distributed ultimate load and with square of span. Now, since beams are continuous, we need to determine the moment coefficients by using simplified analysis proposed by ACI if the conditions which are proposed by ACI are fulfilled, then these coefficients are safe. But if those limitations which we have discussed on slide number 20, they are not fulfilled, they are not satisfied, then the proposed coefficients are not recommended as they may become unsafe. Now, one by one, we want to discuss ACI proposed moment coefficients for different continuous beams, and in picture B, C, and D, you will find out that based on different end conditions at the exterior support at the discontinuous end, these coefficients are summarized. For example, look at the picture B on slide number 21. They are summarizing not only moment but also shear coefficients for a beam in which discontinuous end is actually unrestrained. What it means? That there is no monolithicity between the beam and the support, or between the slab, if it is one-way continuous slab, and the support. I can give you one practical example, that beam resting on masonry support, RC beam resting on masonry wall or masonry column. So there is no integration between the slab or beam and the support. It is free to rotate. Movement will not be restrained. So that is the reason ACI has proposed movement coefficient. They are using C for coefficient. The terminology is C stands for coefficient and subscript M stands for movement coefficient, and subscript V will stand for shear coefficient. So when a continuous beam on the end will rest on masonry column, or there is no integration between the beam or slab and the support, Cm will be 0. While for shear, the coefficient will be 1. What it means? That in order to calculate the shear force, what you will do, you will simply multiply the load with the span and you will divide it with 2, and the coefficient CV will be 1. So it means exterior support will take exactly half of the uniformly distributed load as the reaction, because CV is 1 and Cm is 0. There is no hogging moment and negative steel is not required on top because movement is 0. If this is the end condition, then the mid span, so this will be the mid span of the end span, then the mid of the end span will take the coefficient for positive movement. I will use M with the subscript positive, VE. So M positive is actually equal to 1 over 11 into WU into Ln square. What Ln square means? It is the clear span face to face of the support. So let me rewrite here neatly that I am talking about the positive movement in the end span at the mid of the end span, because positive movement will be maximum over there. So this 1/11 I have picked up from ACI proposed coefficients, because all the limitations, which were 5 limitations summarized on slide number 20, are fulfilled. And then I'm allowed to use them, and I got the moment magnitude by multiplying load with the square of spans with the coefficient Cm, which is 1/11. Then comes exterior face of first interior support. So ACI has proposed for hogging movement, for negative movement, the movement coefficient. So I will use M negative, and Cm is actually 1/10. And again I will multiply it with the load uniformly distributed, and then with the square of the clear span. You can use Ln to indicate that it is the clear span face to face of the support. It is important to note that if the beam has only two spans, although in this picture they are indicating that beam is continuous and beyond two spans there may be 4 or 5 spans, it is shown continuous. Suppose if we are dealing with only two span beam, then this 1/10 will become 1/9. So the face of the support and right terminology will be exterior face of the interior support, because if there are two spans, it means there is only one interior support. So we may state exterior face of interior support. So this will become exterior face of interior support, and this will also become exterior face of interior support, because in case of two span beam there are only two spans. So the interior support on either side will have the exterior face, and for both of them the coefficient proposed for hogging movement is 1/9. So more movement will be demanded in case when spans are only two. And further it is mentioned it will become 1/10 if 3 or more spans, what is shown in this picture. And under that CV is given 1.15. So it means in order to perform shear design, the face of the support will take 15% more than the exterior support. So on exterior support CV was 1, but first interior support will take CV 1.15. So in comparison with exterior, first interior is taking 15% more load, and this approximate estimation will be used to determine the design shear further at a distance d from the face of the support. So you can plot the shear force diagram with this proposed coefficients, like I may draw it like this, that you have W ln by 2 over here, and here you have 1.15 W ln by 2 over here. And then you can move to a distance d from the face of the support, get the design shear by subtracting from this shear force magnitude the uniformly distributed load minus d. So load into distance d will be subtracted from this 1.15 W ln by 2. So what you will get as VU design, if the conditions for the design shear that you are allowed to take the design shear at distance d from face of the support, then it means what you will get first, it will be the 1.15 WU ln over 2. So this is at the face, then minus WU into D. So this will then give you actually the design shear if our cross section will be at distance D. And for this case, you will subtract from WL by 2 minus W into D to get the design shear. So if you have this beam with 3 or more spans, then it is important to note the interior supports like this one and this one and this one. So the faces of interior supports will get coefficient 1 over 11 for hogging moment. So the exterior face of first interior support was taking 1 over 10, but all other faces are taking relatively less hogging moment demand, and you will determine the demand on the other faces of interior supports with the coefficient 1 over 11. And if you have 5, 6, 7 span beams, so for all other faces you will take 1 over 11. And look at the shear. Shear is CV is all 1. So it means WL by 2, WL by 2. So all half will go to the either end. And one more important section is mid span of the interior spans. So mid span of interior span will take the positive moment coefficient 1 over 16 into WU into ln square. So all mid spans will take M positive with coefficient 1 over 16. So picture B actually describes a continuous beam with end resting on masonry or non-monolithic support. So it means discontinuous and unrestrained. While picture C and D below describes movement and shear coefficients, where discontinuous end is integral, is monolithic with support. In picture, discontinuous end is integral with the support, and support is a spandrel beam. So it means this beam resting on another beam, which is spandrel beam. While picture D describes discontinuous integral support, where support represents a column. So beam is framing into a column. Or if it is a slab, slab is framing into a, I may say, a RC wall. And in this case, slab is framing or resting on the edge on a spandrel beam, because these coefficients are simultaneously applicable for the one-way continuous slabs. Because you can assume this is a unit strip of one-way continuous slab, because unit strip of one-way continuous slab means it is a unit strip beam which is continuous over the supports. Behavior will be just like a beam, because curvature of beam and one-way slab is one way. So look at the difference. If end is integral with the spandrel beam, hogging moment is now not zero. It will take m negative with the coefficient 1/24. Along with WULN square. Unlike non-monolithic picture B, where it was zero. But if it is resting on column, then m negative will be calculated by 1/16 rather 1/24. So it is 1/16. And based on these conditions, there is a change in the end span positive movement. So unlike picture B, where the end span positive movement was with coefficient 1/11, here in case C and D, where beams are framing into spandrel beams or RC columns, the end span positive movement by the coefficient 1/14. And it is also mentioned that for exterior face of first interior support, not only the movement but also the shear coefficient is same as it was in picture B. However, if this beam is a two-span beam, so just like for picture B, it was stated that the hogging moment will then be based on 1/9. The same is given even end condition. So it means for two-span beams, it is fixed whatsoever the end conditions are. Your interior support will take hogging moment out of magnitude 1/9 into load into span square. While for 3 or more spans, there is no change in picture B, C, and D. Not only on exterior face of interior support, but also on other faces. Absolutely no change. Not only in flexure, but also shear. And in positive, it remains the same, 1/16, 1/16 for all other spans at the mid, where maximum positive movement will be present. It will be calculated by the coefficient 1/16 whatsoever the end conditions are. And negative movement for all interior supports whatsoever the end conditions are will be calculated by 1/11. So let me stop here for a few minutes because some students have requested me to please give few minutes break during the lecture, so I have stopped recording, so you can ask me questions with reference to the first hour discussion on the topic continuous beams analysis. Is CR online?
Yes, sir.
Okay. So the first hour recording is uploaded. Now I will start recording from this slide onward. So the summary of coefficients with the different end conditions is given on slide number 21. Hence, one table is also copied on slide from ACI Court 2019 publication. In chapter 6, table 6.5.2 also summarizes the moment coefficients, which you can review keeping in picture the discussion made on slide number 21. So there is one additional row here for slabs. Let me use pointer. Slabs with spans not exceeding 3 meters and beams where ratio of sum of column stiffness to beam stiffness exceeds 8 at each end of span. It means too much stiff columns. So fixity is relatively high. So that is the reason they have little modified for such conditions the coefficients for the face of all supports satisfying A or B. So in that case, rather than 1 over 11, it is suggested that for slabs not exceeding 3 meter and in case of beam column frames where the stiffness ratio of column to beam exceeds 3 at each end of the span, then you are allowed to modify the coefficient from 1 over 11 to 1 over 12. It is important to note that if you disagree with these coefficients or you prefer to go for any classical method, you are most welcome. You can perform moment distribution or any other method of your choice to solve the continuous beam. And currently, finite element programs are quite popular, and we can use some commercial software to solve continuous beams. It is further mentioned in note 1 to calculate negative moments. Ln will be the average of adjacent clear span lengths, because we have studied that two adjacent span can differ within the limit given by the ACI code. So if adjacent spans are within the limitation, so then what ln you will take, it is suggested that for negative moments, average of two adjacent spans. For example, one span is 4 meter, other span is 4.1 meter. You can take average of both to determine the negative moment. Now this detail of a continuous quite useful to capture the problem. What you need to steel not only longitudinal, flexural, but also shear. Good picture to understand describes deflected shape So based on demand, that where there is a tension line of slab, so there no slab present, so you can assume a rectangular beam without of slab on top. So there is no line shown. But still, if for this rectangular beam, even if it will be a T beam and crack location, orientation, flexural or flexural shear cracks are shown in this picture, and accordingly the reinforcement is drawn where there is a tension steel is present over there, and our role, but also on the exterior support, because beam there will be the steel of the column present, longitudinal steel, how to design, and the steel of beam, they are present over here, so this will become anchored within. At the movement diagram, under typical uniform distributed loading, if I take you slide number 21, it was 1/16, and the positive in that case is just this we discussed. Knowing the load present on the beam, imagine that on this beam, based on load transfer path, if it is a part of a one-way or two-way slab system, you have determined the uniformly distributed load on this beam. You may assume 100 kilonewton per meter is the ultimate load on this beam per unit length, 100 kilonewton per meter. And if you are given with the clear span, or you can calculate at your own if you are given with the architecture working drawings, all imagine that all spans are equal and all spans are 5 meters. So it means your analysis becomes too simple. You just need to select the right coefficient, like 1/16 into 100 into 5 square will give you m negative at the exterior support. Then 1/14 into 100 into 5 square. So in this way you can calculate all the moments. And now point will come that if you calculate mechanically how much sections you need to handle, first section what you want to design will be this one, hogging section with coefficient 1/16. So let me first take all the hogging sections. So first section, what you will be designing will be with the moment magnitude 1/16 into span square into UDL. Then comes the second negative 1/10 and 1/11. It is quite possible these sections are very close. So finally you will providing on both faces the steel according to the demand 1/10. You can bend some steel or you can curtail if development or the anchorage of the steel is done, but this will be our topic in PRC2. But at this stage you can assume that out of 1/10 and 1/11, suppose 1/10 gives you 90 kilonewton meter movement and 1/11 gives you 85 kilonewton meter movement, so you will obviously provide the hogging steel over here with reference to the coefficient 1/10. So you need not to curtail the steel on face where the coefficient is 1/11. If the support is not too wide, you can provide the same steel on both faces. So it means first you calculated the section with coefficient 1/16, then you calculated the steel with coefficient 1/10, and then you calculated the steel with coefficient 1/11. So three minimum, I would say, three hogging sections you have to handle in continuous beams. I'm talking about the situation where spans are equal, all spans are 5 meters. So you will not get any different movement magnitude for all other interior supports. So 1/11 will remain for all interior supports. First interior support will take 1/10 and exterior will take 1/16. And beam is framing into column like in this picture. And then comes the dealing with sagging regions. So you calculate 1/14 movement over here, positive. And then you have to handle another section with positive movement with the coefficient 1/16. And for all other mid span, it will remain 1/16. So mechanically, if I count, I have to deal with 1, 2, 3, 4, and 5. Rest is repetition. So if the other end of the beam also is framing into the column, the other extreme end will also get 1/16. So it means minimum I have to deal with 5 sections when beams are 3 or more spans, and spans are equal. So in picture D, one technique of steel layout where we bent up the positive steel and we bring it into the negative domain, which is now not very much commonly practiced, and a separate steel for negative and positive regions is provided like it is shown in picture C. One advantage of this bent up is that bent up will arrest the diagonal shear crack. So normal to the crack, bent up can provide stitching action, but to execute detail this steel is quite tedious, and now it is very much less practiced, and provision with separate layers for positive and negative as shown in picture C is more practiced. Also, you can imagine that for deep beams, this angle is 45. So it means when you will be dealing with bent up, you need a long span to traverse when you are providing the bent up at 45 degree, and even to bent up larger dia bar is not so easy. So currently more is the separate layers for negative and positive steel is practiced, and it is easier to lay out and to detail steel in separate layers, because in bent up you will be having less choice, because you need to bend up the positive steel in the negative domain, and the bars which you brought from positive to negative then will be counted as the area required in negative. If it equals your demand in negative by bending up the steel from positive to negative, then it is fine that whatever was bent up, it was providing us the required area. But normally, hogging demand you have seen is more than the sagging demand. So additional bars we need to again select, and in this way not only bent up, because 50% steel we may bend up from positive to negative region, and then 50% from either span, adjacent span, and then the remaining additional bars we need to select to cover up the deficiency. So this, as I said, is not very much practiced now. So we can detail the separate layers. And this one picture I have taken from McGregor, where there is no bent up and negative steel is separate and positive is present at the bottom of the beam, and also the slab steel is laid along with some piping for steel wires, for electric wires, and steel layout is in progress. Formwork is being placed, so it is not the picture which indicates that now the slab is almost ready to be poured with concrete. Still work is in progress. However, in this picture you can find not only flexural negative steel but also the shear rings ties, and finally when you will pour the concrete at the junction between the slab and the web, there is a monolithicity. So slab along with the beam web will be poured simultaneously, and T-beam action will develop. So there is no joint between the beam and the slab. Columns steel is also present, and I want to discuss in this and in next lecture solution of a problem of continuous beam. So this example I just copied a solved example from chapter 4 of your concrete structures. In SI units. So while solving this problem, I want to discuss different steps which are required to analyze first a continuous beam and then finally to design the different sections. So the statement is very simple. While solving this problem, I will also discuss that if data is not directly given, like in this problem, then what additional steps you need to follow. For example, here in this statement, it is stated that a slab system, roof slab system, consists of 9 by 9 inch wide columns spaced at 5 and 3.5 meter in two mutually perpendicular directions. So the first statement is with reference to the column layout. For example, what is stated that you have a slab system in which, if I consider that this is north south direction and it is east west direction, so along north south columns are spaced at interval center to center distance 3.5 meter, and along east west at interval center to center distance 5 meter. So it is mentioned more than 3 spans in east west direction, which are at interval 5 meter center to center, and in north south direction it is stated that more than 2. So it means when we talk about more than 2, it means that 1/9 coefficient is no more applicable, because we learned that for 2 spans interior support will take hogging moment 1/9 with coefficient 1/9 into load into span square. So this is one hint given in the statement that you have columns spaced in 2 orthogonal directions at interval 3.5 and 5 meter respectively. And in suppose along north-south direction we have more than 2 spans, while on east-west direction we have more than 3 spans. This is direct question. And further it is mentioned beam run in both directions over the columns, having more than 2 spans in each direction. So it is further stated that keep in mind along north south or east west you have spans more than 2, maybe 3 or more spans, and beams are running on column center line. So it is a beam column slab system. We will learn in PRC2 that there are some slabs in which beams are not present. Without beams, slabs are directly resting on columns. But here, since our topic is beam design, so we want to deal with such slab systems in which continuous beams are running on the column center line. And columns given are 228 by 228, which is almost 9 by 9 inch column size. Now it is stated that design first interior long beam. So actually you are asked to design this beam. First interior long beam. It means the beam which is running on column center lines, which are spaced at 5-meter interval. If you are asked to design first interior beam running along the shorter span, then it means you are actually asked to design this beam 3. So it is along north-south direction and it is the first interior beam. I can say that this is B1, B2, and if this one is B3, then this will become B4 because edge beam will have half of the load than interior. So along short span, B3 and B4 will be different from the beam along long span B1 and B2. So in order to design this slab system, practically you need to design all these beams, not just B2, but you have to design B1, B2, B3, B4. And luckily here we have spans equal. If spans are unequal, then we need to analyze each beam and accordingly we need to design. Definitely as a structural engineer, you will be required to design the slabs. If they are in all the slabs 3.5 by 5, they are actually two-way slabs. So the corner slab, edge slab, interior slabs. So you will design as structural engineer all of them. First, obviously, you will design the slabs, then beams, then you will design the columns, and then footing underneath. So as structural engineer, actually it is your role to design all of them. So we are at the moment only talking about B2B, and question is little straightforward. They are saying factored slab load is 12 kilonewton per meter square. So just to avoid additional calculations, because if you are the structural engineer, first you will select the slab thickness and you will design the slab. Knowing the floor finishes present on slab, you need to check architecture working drawings, that on section drawn by the architect, how much is the thickness of the floor finish present on the slab. Slab thickness will be decided by you, and floor finish thickness will be decided by the architect. Type of the floor finish and the corresponding thicknesses. That should be given on the architectural working drawings in the sectional drawings of the building. So your role will be first to design the slab, and you will design the slab obviously by knowing floor finishes and the live loads. Once slab is designed, then you will be able to get this value 12 kilonewton per meter square, because you will be knowing thickness of the slab. You will multiply the thickness with the density of the concrete, and you will multiply it with 1.2 load factor. Then you will be multiplying the live load with 1.6, and because live load is directly given in terms of pressure, floor finish will be given in terms of thickness. We will also multiply that floor finish with density to get the pressure, and you will multiply it with 1.2. So while doing this much effort, you will get finally, after doing this much effort, you will get finally this value of factored slab load. You may say it is QU, given to you directly. But in your projects, like maybe in BSc project or in your subject in 8th semester, sorry, in 7th semester DOS, you will be asked to design complete building. So let me stop here, and in next lecture I will continue from this slide onward. Assalamu alaikum.